topic. Hello. What was the topic again? Hello, this is pizza service. What is your order? Oh no, wrong number. Not again. Hello, sir. What was the topic again? Again? Your topic is Newton's law of gravitation. How many times do I have to tell you? Oh, yes, ma'am. I remember the topic. I was making sure if you remember it as well. So, our today's topic is Newton's law of gravitation. Newton's law of gravitation? What is that? Have I heard it before? I forgot the script again. Again, you were given a simple task. Anyways, never mind. You can go. I'll continue the topic. No one understands me. I will leave. Hello, friends. So, yes, I will need to continue with this. So, let's get started.
As the story goes, once Newton was sitting below an apple tree. Suddenly, an apple fell. Seeing that apple, he wondered why the apple fell vertically downward. He started to think why they don't fall at some angle, or why they don't fly off in a horizontal direction, or fly upwards. After much thought, he concluded that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. Hence, the apple falls vertically downward. This force is nothing but gravitational force. Newton thought that if the force of gravitation acts on apples on the tree at different heights from the surface of the earth, can it also act on objects at even greater heights, much farther away from the earth, like satellites or moons? Can it act on even farther objects like the other planet and the sun, or the universe? The answer to all the above question is yes. Newton formulated a law called as universal law of gravitation. The law states that every object attracts every other object with a force whose magnitude is directly proportional to the product of their masses and inversely proportional to square of distance between them. Consider two masses m1 and m2 separated by some distance r in between them. Then there will be a force of attraction acting between these two bodies. This force of attraction will be directly proportional to the product of their masses and inversely proportional to square of the distance between them. On combining both the equation, we get F is proportional to m1 into m2 upon r square. On removing the proportionality sign, we get a constant g, where g is called as universal gravitational constant, and its value is equal to 6.67 into 10 raised to minus 11 Newton meter square per kg square. The value of g was first experimentally measured by Henry Cavendish. Now here comes the question. As per Newton's law of gravitation, an equal force of attraction is acting on both apple and the earth. Now the question is, does the apple move towards the earth, or the earth moves towards the apple, or both moves towards each other? Well, the answer is simple. As per Newton's second law of motion, force is equal to mass into acceleration. Hence, acceleration equal to force upon mass. That means we can say that acceleration is inversely proportional to mass. That means that more the mass, lesser will be the acceleration, and vice versa. Average mass of an apple is around 100 grams, that is 0.1 kg, while the mass of the earth is 6 into 10 raised to 24 kg, that's 24 zeros after 6. As the mass of the earth is very large, hence its acceleration is negligible. Hence, it is apple that is accelerated towards the earth and not the earth towards apple. Now, another question arises that if there is a force of attraction between every object, then why we are not getting attracted towards each other? Or why the surrounding object doesn't come at us flying? The answer to this question is, even though there is a force of attraction existing between us or surrounding object, this force is very weak as compared to the force of attraction provided by the earth. Hence we are all attracted towards earth and not towards each other. So that concludes the topic. See you next time.